So now that we know how to calculate z-scores, let's talk about how they're used and why they're really important. Z-scores are standardized values that have no units, and that's what allows us to do the comparison. So we can compare things with different scales, with different units, or even from different populations. So let's say, for example, that the ACT and the SAT scores we want to compare. So the average ACT score is much different than the average SAT score because they're calculated in different ways. But we can compare the ACT and the SAT of two different test takers by calculating their z-scores, because those z-scores have no units attached to them, but they're assumed to be normally distributed and so therefore are comparable. Z-scores are also useful because they can tell us how unusual a data point is. So for example, we had a student in our previous data set with a test score that was really low and below average. Let me pull up the scores here. We can see that their class grade was only 2.2, and that was because this student stopped coming to class pretty early on. The calculated z-score for this student was -5.31. The way that you interpret this z-score is that it's the number of standard deviations above or below the mean. So because they had a negative z-score, you would say that this is 5.3 standard deviations below average, whereas a positive z-score would be above average. Now 5.3 doesn't sound like very much, but let's get an indication of how big a z-score needs to be unusual. The larger a z-score is, the more unusual it is. But we can use what's called the 68, 95, 99.7 rule to tell us how unusual a data point might be. The rule comes from what's called the normal model, and we'll talk about this in a minute. But first, let's go over the interpretation. 68% of the data should fall within one standard deviation. The sigma here represents the standard deviation. And remember, we've calculated the z-scores so that the standard deviation of the z-score is exactly 1. So falling within one standard deviation above or below the mean, we should see 68% of the observations. 95% of the observations should have a z-score between -2 and +2. So anything that falls between -2 and +2 is not that unusual because 95% of the data should fall between those two numbers. Anything greater than +2 or less than -2 is going to be kind of unusual because only 5% of the data falls outside of +2 or -2. This is even more so true for 3 standard deviations away. So that would be a z-score of greater than +3 or less than -3. 99.7% of the data should fall between -3 and +3. So something that's greater than +3 or less than -3 is extremely unusual and is only 0.3% of the data set. Now where are these numbers coming from? They're coming from what's called the normal model. The normal model is just this formula, and what it does is it calculates the area underneath the curve that I just showed you. Now you don't have to memorize this formula, but what you need to know is that what we're doing is calculating the area underneath that curve. Mu here represents the average, which we assumed is 0 for our z-scores, and then sigma is the standard deviation, which we calculated to be exactly 1 for our z-scores. And what we're doing is we're plugging in different z's. Here the x represents those z-scores, and we're getting then the area underneath that bell distribution, or what we call the bell curve. So how do we get numbers from this formula? Well, there's a couple of different methods we could use. The t-tables provides us the area underneath the curve for specific z-scores. I'll show you how to use these z-tables in a little bit, and I've provided one below. The z-calculators online, the internet provides plenty of. These calculators simply calculate this formula for you so you don't have to memorize it. However, in some instances, you'll have to specify that the mean is 0 and the standard deviation is 1 to make sure you're calculating exactly the standard normal distribution. Now let's talk a little bit about how you use a z-table. Say, for example, we calculated a z-score of 2.54. We can find the area underneath the curve below that score by looking at the row for 2.5. That's our first digit, and then the second decimal place is 0.04. So the number that we calculate is 0.005. That is the area below the curve, the normal distribution, below negative 2.54. What this number represents is the probability that you would see a data point that has a z-score of 2.54 or something even more negative than that. So the first column shows the z-scores that we could potentially calculate, and the first row shows the second decimal place of that z-score. Everything in the middle here then are the different probabilities associated with those z-scores. And you can see here we're only looking at negative z-scores in this table. The highest the probability goes to is 0.5. And this is because for a z-score of exactly 0, we would only get 50%. So everything that falls below this curve is exactly 50%. If we look at the other page of our z-table, we look at z-scores that are positive. Again, we're looking at everything below these positive z-scores, and so all of these have to have probabilities that are greater than 50%. So you can see that a z-score of 0.00 has a probability of exactly 0.50, whereas anything greater than a 0 z-score is going to have a probability that's much greater than 50%. And you can see that these go almost all the way up to 0.99999, so it almost goes up to certainty. So that's how you use a z-table and the basics behind it, but it'll become easier to use them once we start doing problems with them. To give you an idea of what problems we might use them for, we can answer all different types of questions. So say we want to know what percent of people have an IQ greater than a certain value, or what percent of batters have a batting average above 0.25. This is a specific statistic, and we can answer questions about greater than or less than specific values. We can also use the z-tables to look at values between certain ranges. And so that's what these z-tables will be used for, is to look at certain percentages or certain probabilities that we're trying to calculate.